How are we doing?
Pretty good.
Pretty good. Any questions on anything? Is there homework due?
Yes.
Yeah.
We both
I'll staple it. Thank you. Pardon me. What questions do you have? No questions?
There's not another question set for you to read off,
Gotcha.
but jokes already used.
Yeah, that's true. That is true. What's that? I just heard a laugh. Before we get started, one thing I will encourage everyone to do is if you haven't already, vote if you're able. I know some people aren't from here, but if you're able, vote. One thing I will say is that I think it's exceptionally important for young people to start getting more involved in politics because it's going to affect you the most going through the rest of your lives. So make a plan, vote your conscience, whatever that happens to be. If you want to know my opinions, I'm happy to give it to you, not in class. But if you want my opinions, I'm happy to give them, but vote, be involved. And in particular, as you get older, you'll realize that the local elections may even have more effect on you than the national elections do. So pay attention to those as well. School board elections, city elections, county elections, those kinds of things are also important. County boards determine property taxes, for example, where money is allocated to different places in the county. Same thing with the city. School boards determine school policies, those kind of things. So pay attention to those elections too. I will encourage you to do that because, yeah, there's lots of stuff going on. So, and like I said, it's going to affect you all a lot longer than it's going to affect me. So make a plan and vote if you haven't already. I actually have to go fix my vote because they said I did a mail-in ballot and they said my signature didn't match. So I need to go in and go cure my ballot. So that isn't like fun. I don't know. I've never had that happen before. So yeah, well, you know what? Honestly, at least they're checking the signatures.
Yeah.
So there actually is a process to make sure that the people who are supposed to be voting are actually voting. So that makes me feel a little bit better about that. No, I just have to go down to the county clerk's office and go fix it, but I'm actually happy that they're doing that. So anyway, I'll get off that particular stuff. I heard that a couple of the different student organizations on campus are doing the March to the Polls. Black Student Union, Latino Student Union, I think, are both going to do that on Tuesday. Kind of, doing the symbolic gesture like the blacks did in the 60s when they weren't able to, they were being turned away lots of times. So I thought that was kind of cool that they're going to do that. So anyway, I just heard that yesterday at the faculty meeting, so that was why I was sharing. I thought it was really cool. All right, so let's continue on with our discussion last time. And again, this is the last section that'll be on the exam that you'll take in a couple of weeks. So again, to remind, the 12th is advising day, so we won't have class that day. And I know at least two of you are going on the trip to St. Louis, right? So we won't have class on the 14th either. So, but you can schedule your exam at any point during that week. I do not know when our final exam is scheduled yet. As a matter of fact, usually there's a link on our side of the MU Online stuff when you go, and it says faculty exam schedule, and that link isn't even there. Even if they haven't been scheduled yet, that link's always there, and it's gone. So I don't know what that means. I don't know if that means they're working on it. I don't know if that means that, like, out of sight, out of mind, I'm not going to worry about it. But as soon as I know, my intention, though, I think last year they came up kind of with a master schedule of if your class meets at this time, then your final should be at this time. And I think ours was scheduled for Tuesday of finals week. But my intent is to let you do it anytime up until Wednesday of that week. And then you give the other finals on Wednesday anyway, if that schedule holds true. So do the same kind of thing. Just schedule a time with me, and you won't have to necessarily do it during the finals exam time for this particular class.
Is the final cumulative?
Yes. Yeah. But we'll talk about specific things to worry about.
Yeah.
I would what my intent would be kind of definitions, example stuff would be old stuff. Then the new stuff that we cover from probably starting today through the rest of the semester would be the stuff that we want proof focused, so that you can worry about definitions, examples, but not necessarily the proofs for the earlier stuff, and then worry about the proof stuff for the new stuff. Does that make sense? Yeah. Cool. All right. So last time the theorem we talked about was that if I is an ideal of R, forgot a verb. Oh, for heaven's sake. I don't know why it doesn't like to do erasing. If I is an ideal of R, then I is prime if and only if R mod I is an integral domain. And we did some examples last time of this theorem, but I don't think we proved it, if I remember correctly. I don't think we actually proved it. So let's go. I want to go through the proof. If we proved it last time, I don't want to do it again, but I don't think we did. I think we just talked about using it as examples, and I did a definition of what a maximal ideal is, which I can still see at the top of the screen. All right, so let's do the proof here. So since it's an if and only if, let's work with our go left to right and then right to left. So let's suppose that I is prime. So remember what it means to be prime again? What's our definition of being a prime ideal?
The product is in the ideal of it. One of the elements is in the ideal.
Yep, that's exactly right. So if a product is in the ideal, then one of the factors has to be in the ideal. And that's our extension of being a prime number, essentially, right? So one of the properties of being a prime number is if a prime divides a product, then it divides one of the factors. And so that's just an extension of that idea. We talked a little bit about why that was an extension of the idea using principal ideals. Talked about that last time. So again, so it's if a product is in the ideal, then at least one of the factors has to be in the ideal. So I want to show that, assuming that it's prime, then the factor ring is an integral domain. The quotient ring, factor ring means the same thing. So remember, integral domain has to be commutative ring with identity and has no non-zero divisors. I didn't write down the assumption that R is a commutative ring with identity, so we'll just assume that R has to be commutative with an identity. Otherwise, we can't get an integral domain necessarily out of it. All right, so the idea here would be, if I want to show that it has no non-zero divisors, I want to assume that we start with a product that's 0 and then show that one of the factors has to be 0. Okay, so let's suppose that. So I say further. Let's suppose that A plus I times B plus I is equal to 0 plus I. So I have a product in the factor ring that's equal to 0 in the factor ring. So remember again that our elements in the factor ring are cosets generated by elements of the ring, so they look like that A plus I piece. The 0 element in the integral domain is the coset generated by 0. It's just the ideal. And that was what we were talking about when we were looking at trying to determine distinct elements in a ring. distinct elements in a factoring, one of the things we did was we said treat everything in the ideal like it's 0, and then figure out what's left. You get the non-zero elements. All right, how do we do the product in the factoring? When I take two cosets and multiply them together and get a new coset, how do I generate that new coset? What is a plus I times b plus I equal to? Yeah, it's ab plus I, right? So we would have ab plus I is equal to 0 plus I. How do you know two cosets are the same? What has to be true if you have, let's write it off to the side here, if you have C plus I is equal to D plus I, what has to be true?
C minus D is
Yeah, the difference between the two is in the ideal, right? If they generate the same coset, then their difference had to be in the ideal. So this statement here is saying that AB generates the same generates the same coset as 0. So where does that say AB lives? In I. Good. So because AB minus 0 would be an I, or AB is an I. Now I have a product that's in I. What are we assuming that? What kind of an ideal are we assuming that I is? Prime. So what does that say now? Good. So since I is prime, A is in I or B is in I, how would we convert those statements into an equation involving cosets? I want to turn A being in an I into some equation involving cosets. What can I write? For example, what can I say A plus I is equal to? 0 plus I or good. Well, yeah, one or the other has to be true, right? So let's go back up to what we started with. We assumed we had a product of two cosets equaling the 0 coset. We showed that one of the cosets, one of the factors, has to be 0. Isn't that exactly what we need for integral domain? If a product is 0, one of the factors has to be 0. So hence, R mod I is a domain. And again, if I just say the word is a domain, I mean integral domain. That's just shorthand. Mainly because there aren't other types of domains in algebra besides integral ones. That okay? Now we need to go the other direction. But the other direction, I think we could just almost write the same kind of things. We want to suppose. What happened? That was weird. I don't know why this room I have so much issues with the computer. I teach on this thing in my other 3 classes. I swear I do. Okay, so let's try this again. Let's pull this out. Let's pull this out. Put it back in again. Where's your problem?
Can you hit connected devices or do you need like a remote to do that?
Oh. Let's see, I have a remote. PC. It really does not think it's connected.
What the heck?
Alright, so we want to go the other way. Well, suppose that R mod I is a domain, and we want to go the other way. So again, the defining characteristic for being prime is if a product is in the ideal, then one of the factors has to be in the ideal. What came out?
There's like 37 Diary of a Wimpy Kid books, and I was just saying like I feel like one just came out and it came out the 22nd.
Oh.
So it actually did just come.
It's late.
Sorry, that was me.
That's all right. That's okay. No worries. All right. So again, the defining characteristic for being prime is if a product is in the ideal, then one of the factors has to be, right? So we'll start with a product being in the ideal. The condition that we have to work with is that R mod I is a domain, so I need to convert this statement about an element being in the ideal to some statement in the factor ring. But just like before, how can I convert this to a statement about cosets? So that's what we're trying to get to, right? We're trying to get to that, use the fact that we get a zero thing in there. But I just want to convert this statement into one about cosets. If an element's in the ideal, how can I convert that to a statement about cosets? Like what we did here. There we go. Yep, AB plus I is 0 plus I. I want to use the fact that we're in a domain, which talks about products being equal to 0. Can I change the left-hand side into a product? You know what would be? Yeah, it'd be A plus I times B plus I is equal to 0 plus I. Good. Basically, this proof is an exercise in rewriting definition or rewriting things in terms of almost definition ideas, right? Just making sure you can connect the ideas together. We now have a product equals 0, equaling 0 in a domain. So what does that tell you about one of the factors? One of them is equal to 0. So since R mod I is a domain, we have A plus I equals 0 or B plus I equals 0. But I want to now convert this back to a statement about something about the ideal, right? Because we're trying to show the ideal as prime. So, oops. I forgot my plus I on the end of these, didn't I? Sorry. I want to convert this back to a statement about the ideal, the elements being in the ideal. So the first equation, if you had A plus I is equal to 0 plus I, how could you rewrite that in terms of being an element of I? Yep. A is an I, and the second one says B is an I. And that's exactly what we needed to say that I is prime. Does that make sense? Pardon me. And again, we've shown some examples of why it might be easier to get to something being prime using homomorphisms and kernels of homomorphisms. And we'll do another example like that. But let's also talk about how we have a similar theorem for maximal ideals. So remember we talked about what a maximal ideal is. Basically, if you have an ideal that's maximal, there's nothing else between that ideal and the whole ring that's also an ideal, right? So if an ideal contains a maximal ideal, either it is the maximal ideal itself or it blows up to the whole ring. That was what we meant by maximal. There's a similar theorem to what we just proved here. So we're going to let R be, again, a commutative ring with identity. And we'll let I, and I'll call it M this time, M be an ideal of R. Then M is maximal if and only if R mod M is a field. A little bit stronger than being an integral domain, right? Fields are also integral domains, but they have the added benefit that any non-zero element has a multiplicative inverse. We don't get that in every integral domain, right? Let's do this with an example before we go through the proof. So, okay, fine. I'll leave that as messy. As an example here, let's say we look at the ideal generated by 5 in the integers. Let's start there. I want to show that this is maximal. So one way to do this is to take a homomorphism that goes from Z to some field where this is the kernel, where this is equal to 0, basically, basically it's equal to 0 when you do the homomorphism. It's the kernel of the homomorphism. So if I take my homomorphism that goes from Z to something, and I want to make all multiples of 5 equal to 0, what ring do you think I might want to map to? If I want to make all multiples of 5 equal to 0, what ring do you think I might want to map onto? Z mod 5, good. So we'll take phi going from Z to Z mod 5, and we'll define it by phi of x is equal to x mod 5. Kind of that natural homomorphism, if you will. From properties of modulus, we know that this is a well-defined homomorphism. It definitely breaks up over sums and breaks up over products. What is the kernel? So the kernel is a set of all x such that x mod 5 is equal to 0. That's what it means to be the kernel, correct? Is everything that maps to 0? Well, what maps to 0? How are you 0 mod 5? What do you have to be? Multiple of 5. So this really is the ideal generated by 5. So by our first isomorphism theorem, if I do Z mod out by the ideal generated by 5, I really get Z5. Z5 here is a field, right? Every non-zero element in Z5 has a multiplicative inverse. The inverse of 1 is itself. The inverse of 2 is 3, because 2 times 3 gives you 6, which is 1 mod 5. 4 is its own inverse. 4 times 4 is 16, which is 1 mod 5. So this is a field. So since Z5 is a field, that means this is maximal in Z. There was nothing special about 5 except for the fact that 5 is prime. Every Z mod P is a field, right? Every Z mod P is a field because we can find a multiplicative inverse. Because every non-zero element of Z mod P is relatively prime to P. So we can find a multiplicative inverse using the linear combination that gives us 1, right? You have AX plus PY equals 1, and I reduce it mod P. That goes away. And now I have a multiplicative inverse for A. So every single Z mod P is a field. So what did that just show? We talked last time about a prime in Z generates a prime ideal in Z. This exact same proof will give you that the primes are also maximals. So every single prime ideal in Z is also a maximal ideal in Z minus 1. There is a prime ideal of Z that is not maximal, and that's the 0 ideal. In an integral domain, it's the 0 ideal is a prime ideal. Because again, if you have a product that's in the 0 ideal, it has to be 0, and we know that a product is 0 if one of the factors is, right? So in an integral domain, the 0 ideal is always prime. In the integers, every other prime ideal happens to be maximal as well. Anyway. But this is how you use this particular theorem. So to give you another example, we talked about this last time, but just to do it again, if you look at the ideal generated by X in the polynomials with integral coefficients, we said that if I take Z adjoin X and mod out by the ideal generated by X, so let's just think about what this says in words, and then hopefully the isomorphism will be obvious. I take the polynomials with integer coefficients, and then I say X is 0. What ring do I end up with? Not quite 0. So if I take all the polynomials with integer coefficients and say X is 0, what do I end up with? The integers, right? This should be isomorphic back to the integers again, right? The integer, the ring of integers, is an integral domain, which means what about this particular ideal? This is a domain, so this ideal is not quite maximal, but it's prime, yeah. Right? It has to be maximal if the thing on the right is a field.
Oh.
Yeah. And the set of integers here, is that a field? No. Okay. So the ideal generated by X is prime, but it's not maximal. If it were maximal, I'd get a field on the end, which it did not. Versus if I take the rationals adjoin X and mod out by X, what do you end up with? Yeah, I end up with the rationals, right? We agree? Yeah. So the rationals are a field, so that ideal is maximal. By the way, if you want the explicit homomorphism that goes from Z of X to Z that you want to use, over here you would say phi of the polynomial is just the polynomial evaluated at 0. That would be the homomorphism that you need. That treats x like it's 0, right? I replace the x with a 0. So that would be the homomorphism that would work. We refer to such a homomorphism as an evaluation homomorphism. This will be a homomorphism regardless of what I put in for the polynomial. Because remember, just the way you define addition and multiplication of polynomials, says just add the outputs and the same thing for the multiplication, right? So it breaks up over sums and it will break up over products. So any evaluation homomorphism, any evaluation function is a homomorphism from the set of polynomials to the ring that the polynomials are over. I know that was a lot of words. Sorry. Okay. All right. Anyway, let's see if we can prove this theorem and then do a couple more problems. All right. So proof of the theorem. So I want to show that if it's maximal, then we get a field. And if we have a field, factor rings a field, we get a maximal ideal. All right, so let's go left to right, and let's suppose that M is a maximal ideal. Oops. I need to show that any non-zero element in R mod M has a multiplicative inverse, right? That's the idea, correct? Okay. So if we further suppose that A plus M is not 0 plus M, I need to find a multiplicative inverse for A. I need to find some other element in R mod M so that when I multiply it, I get the identity. Right? I need to find a multiplicative inverse. All right. If A plus M is not equal to 0 plus M, is A in M? Is it possible for A to be in M if the coset generated by A is not the same thing as the coset generated by M? No. So then A is not in M. All right. Now let's consider this set. I'm going to do all these sums. I'm going to take an element from the ideal and any multiple of A. Okay. A is fixed. A is this element A that I'm talking about over here with the A plus M. But R can be anything in the ring. M can be anything in the maximal ideal. Okay? Our claim here J is an ideal that properly contains M. I don't know why I keep putting an extra hump on my M. Let's just do this and talk about it for the properly contains M. What can I use for R to show that J actually contains every element of that? I said M can be anything and R can be anything. What can I use for R to show that M is inside of J? 0, yeah. If I use 0 for R, then J has all the M's in it, right? Okay. What can I use for M and what can I use for R to find an element that's in J that's not in M? 0 and 1, good. Because I know that A is not in M, right? If I use 0 for M, which is in capital M, because every ideal contains 0, and I use 1 for R, which I can do because R has an identity, right? I get A is in J, which is not in M. Okay? So I'll just write that down. Using R equal to 0 shows that M is a subset of J, and using 0 for M, oops, do it this way, little m equals 0 and little r equals 1 shows A is in J minus M. Hence, M is a proper subset of J. There's the proper containment. Okay? Why do I want proper containment? Well, remember, M is what kind of ideal? It's a maximal ideal, right? So can there be any other proper ideal bigger than M that contains M? No. Okay? So if I can show that J is an ideal, then what does J actually have to be? It would have to be. It says that we have it that it's bigger. What's the only thing that's bigger than M and contains R? That contains M and it's still not. It's R, right? So we'll show that J is all of R. Okay. So let's talk about why this is an ideal. Well, to show that it's an ideal, it has to be closed under addition and absorb ring multiplication, right? Okay. So I'll call it M1 plus R1A and M2 plus R2A be in J. And we'll call it X be in R. Oops, subtraction, not addition. To show that it's an ideal, I need to show the difference of these two elements is back in J again. And when I take one of these elements and multiply it by X, it's back in J again, right? That's our ideal test, correct? Closed under subtraction, absorbs ring multiplication. Elements in J look like elements from the maximal ideal plus element of the ring times A. So I just wrote two different elements that look like that, right? How can I rearrange this subtraction statement to see that this element is back in J again? How do I want to rewrite it? Okay. Yep. Good. I can put the M's together. I can factor out the A and put the R's together. Where does this piece live? That I just put the little bracket underneath. If this is in M, where does this live? Right here. In R. So the whole thing ends up in J again, right? I've got element of M plus element of R times A. Does that make sense? It's closed under subtraction. What happens if I take X times one of these elements? What do we get? How can I rewrite that? What do you think I want to do first with the x? Distribute it. And for emphasis, I'll put the x and the R1 together. Where does x live again? In R. Where does M1 live? In capital M. So I've taken ring element times ideal element. Where does that end up? M's an ideal, right? So if I take ring element times ideal element, where does that end back up again? The ideal, right? So this part, well, that was an ugly looking brace. That's back in the ideal. If I take ring element times ring element, where does that end up? Back in R. Good. Yep. That is two. Those are bad braces. My goodness. So we have element of M plus element of R times A. So where does that whole thing end up back in? J. Hence, J is an ideal that properly contains M. And we just said a minute ago, since M is maximal, we must have J is equal to R. Shoo, that was a long way to get there. I know, there's lots of hard stuff. That's why I'm trying to take it slow. I know it's harder. Okay. All right, we're trying to show that R mod M is a field. So the whole goal of this was to show that A plus M has a multiplicative inverse. If it has a multiplicative inverse, I need to find something to multiply it to get me back to what again? If I want to have a multiplicative inverse, I multiply it by something to get to the 1, right? That's what I'm trying to get to, correct? This is why we want J to be all of R. If J is all of R, then 1 is in J, right? The identity of R is in J, right? We know that there exist, it doesn't matter what I call it, I'll call it M bar plus R bar A in J such that, oops, sorry, not in J, such that M bar plus R bar A is equal to the identity in R. I'll write it 1 sub R just to emphasize that it's the identity. Okay. So far, so good? Okay. So the set J we created is an ideal containing M is bigger than M, so it had to be the whole ring. The identity is in the whole ring, so I can write the identity as something in J. Okay? What happens if I take A plus I times R bar plus, not plus I, dang it, plus M? What happens when I multiply those two things together? Yep, it's A times R bar. I don't need parentheses. Or maybe I do need parentheses because it's not letting me erase them. I didn't need the parentheses, but right, it's equal to that. We agree? Again, we're trying to find a multiplicative inverse for A. If I want this thing that I just wrote to be the multiplicative inverse for A, what do I want to replace R bar with, or R bar with? If I want this to be the multiplicative identity, or multiplicative inverse for this, what does this need to be? 1, right? I need to replace AR bar with 1, right? What up here, how can I rewrite this to see that I really do get 1 there? Look at this piece right here. How do you think I might want to rewrite that? The other way. You're right about the 1 minus.
1 minus A.
Yeah, I want to do it the other way. Good. Okay. We have 1 minus R bar A is equal to M bar. Where does M bar live? Capital M. Right? Now how can I convert that back to a statement about cosets? I have the difference of the two elements is in the ideal. So how can I convert that to a statement about equal cosets?
1 plus M.
Good. So this means 1 plus M is the same thing as R bar A plus M. R bar A and AR bar are the same element. We're in a commutative ring. Hence, R bar plus M is the multiplicative inverse of A plus M in R mod M. I know, that was long, and it's only half the proof. That was only one direction, right? M was maximal, so R mod M is the field. There's a lot, wasn't it? I agree. It's okay, that's a lot. It's okay if you think it sucked. It's fine. What's that? It's only it's an if and only if. We only did one direction, so it was only half the proof. We got to go the other way.
You said that implies the other half is just as long as this.
Yeah. No, it's not. It's actually shorter. We've already put in a lot of the work. Okay. Let's suppose that R mod M is a field. We want to show that M is maximal, right? To show M is maximal, I want to show that if there's an ideal that properly contains it, then that ideal actually has to be the whole ring, right? Agreed? Okay. What special element, when we lands in the ideal, we know that the ideal blows up to be the entire ring? 1, right? So what we're going to show is that if R mod M is a field, and I have an ideal that properly contains M, 1 has to be in it. That's where we're going to go, okay? So let's suppose that J is an ideal of R with M properly contained in J. If M is properly contained in J, what can we find? Good. There exists an A in J with A not in M. If A is not in M, what can I say about the coset in R mod M? If the element is not in M, then what coset do you know that this is definitely not equal to? Good, 0 plus M, good. If it's not in the ideal, then it can't generate the zero coset, right? Now we have a non-zero element in the factor ring. What are we assuming about the factor ring in this case? It's a field. So what does every non-zero element in a field have? An inverse, right? A multiplicative inverse, right? Every non-zero element in a field has a multiplicative inverse, okay? So since R mod M is a field, there exists, I'll call it B in R, such that A plus M times B plus M is equal to 1 plus M. We're almost done. This one's not going to take nearly as long. The left-hand side we can write as AB plus M, right? That's how we multiply two things in a factor ring. We just multiply their coset representatives. How can I convert that coset equation, if you will, into a statement about an element of M? What has to be in M now? AB minus 1. I'll write it as 1 minus AB. But you're right, AB minus 1 also works. What are we assuming that M is contained in? J. So 1 minus AB is in J, right? We agree? Where do we assume A lives? How did we get the element A? It's in J, but not in M, right? So A is also in J. If A is in J and J is an ideal, where does AB live? J. If AB is in J and 1 minus AB is in J and J is an ideal, what element lives in J? 1, right? We have A is in J, so AB is in J, which gives 1 minus AB plus AB is equal to 1 is in J. That was our whole goal, was to get the identity in J, right? Because what does that mean J is equal to now? R, good. So hence, J is equal to R, and M is maximal. So that one was not nearly as long. I only said half because you have two directions, not for the length of the proof. Is that okay? Yeah, not too bad. Page and a half. Where you have a computer and it's just infinite scrolling, right? Scroll, more paper. What's interesting is, at least I find it interesting because I'm old. So, you know what an overhead projector is? Do you have teachers that used overhead projectors? Did they have a little scroll on it? Have you ever seen an overhead projector with a scroll on it? One big, long transparency on a scroll, and you'd have a crank, and you could crank it up. That's what this reminds me of, is you crank it up to get a new sheet to write on, and you crank it up again, and you write on it.
Oh, that's fancy.
Yeah. I had an algebra teacher in high school that used that. She also had a fan in there that sounded like a jet engine when it was on all the time. But yep. Well, yeah, it was a crank on both sides, so you'd have a whole new rule you'd put at the bottom, and as you would write, you'd crank it, and then you run out of transparency, you'd put a new roll on it. I don't know how many people have seen the transparencies are so outdated now because of this stuff that we have. Anyway, let's see. Pardon me. Let's see if we can do a couple of problems here. I want to look at number 14. I'm not sure I'm going to get to the toys today, but that's okay. We'll find out. Number 14. What 14 says that if P is a prime ideal of R, then is P cross P a prime ideal of R cross R? Certainly, we've already talked about that if you've got a direct product of rings and you do an ideal in the first and an ideal in the second and do their direct product, you get an ideal in the direct product. We've talked about that. But this is saying that, I know it's doing P cross P and R cross R, but it's asking you if you take a prime ideal in the first factor and a prime ideal in the second factor, is it necessarily the case that the direct product of the ideals is a prime ideal in the direct product? So again, our definition of being prime is what?
If the R cross R mod P cross P is
Okay, so that's the theorem. That if you do R cross R mod P cross P, it had to be an integral domain, right? Right. That's one way to look at it. So that's a better question: is R cross R mod P cross P an integral domain? That's another way to think about it. Is that true? Okay, let's just think about stuff that we've done before. If I want to rewrite this as in terms of isomorphic, how can I rewrite this? So R mod P cross R mod P, right? We talked about that last time, that if you have an R cross S mod out by an I cross J, you can basically split it up. Okay. Well, what do you know for certain about R mod P? What the heck happened there? What do you know about R mod P? What kind of a thing is it? It's an integral domain because P is prime. What about R cross P, or R mod P on the other one? It's also a domain. Is a domain cross a domain a domain? So in order to be a domain, if you have a product equaling 0, what has to be true about one of the factors? It has to be 0. Can you think of a product that's equal to 0 where not either factor is equal to 0? In general, direct products are never domains, ever. The only way a direct product can be a domain is if one of your if you're doing a product of two of them and one of the factors is a zero ring. Okay. Non-trivial direct products can never be domains because of exactly this. They always have zero divisors. Always. Non-zero zero divisors. Always have them. Okay. So, going back to the original question, is P cross P a prime ideal? No. No. To think about it the other way is exactly the same product. Do I have a product of two elements now that it's in P cross P? If I just ignore this stuff down here, do I have a product of two elements that's definitely in the P cross P? Sure is, right? Because zero is always in any ideal, right? Is this in P cross P? Is 1 comma 0 in P cross P? If it were, where would that say 1 is? Where would 1 live? If this were in P cross P, where would 1 have to live? P. Is 1 in P? No. Is this in P cross P? No. Okay. So I have a product that's in the ideal, but neither factor is in there. So it's not prime. Can I convert this into a true statement? Given that P is an ideal, a prime ideal of R, can you create a prime ideal in R cross R? In particular, can you create two of them? You do them the same way. If I have a prime ideal of R, can you definitely create a prime ideal in R cross R? Yes. And how would you do it? Yeah, so okay, so that's the right idea. I can do P cross R. If you do, if I do R cross R and you mod it out by P cross R this way, what do you think that'd be isomorphic to? R mod P, yeah, it looks like you're canceling, right? Well, you did in algebra class in high school, right? It looks like you're canceling, doesn't it? Yeah. What kind of thing is this? It's a domain. So that means that has to be prime. What would be the other one you could create? Instead of doing P cross R, you could do R cross P, just flip it around. Yeah. So if, in general, if you have a direct product, I can create prime ideals in the direct product by doing a prime ideal in one factor and using the whole ring in the rest of them. And generally speaking, that's the only way to do it. If I want to create a prime ideal in the direct product, I better have a prime ideal in one factor and the whole ring in the other factors. Because again, of this property here. I can create things that multiply to 0 by using the multiplicative identity, and I know that's not in my ideal. So I can create non-prime things. Does that make sense? Cool. All right. Let's do another one, because you're enjoying this so much, I see. This one is just an example that shows, pardon me, that shows that we need an identity to talk about maximal, to talk about the theorem that we mentioned. So we're going to let, I'll call it E be the even integers. That definitely does not have an identity. And we'll let M be the multiples of 4. Is M a maximal ideal of E? Well, what things doesn't M include? Let's put it that way. What elements of E does M not include? 2. What else? Yeah, one's not neither of them. What are things in E that aren't in M? 2 isn't. 6 isn't. 10, 14, right? Multiples of 2 that aren't multiples of 4. Can I throw something that's not a multiple of 2? Now, if I take something that is a multiple of 2 that's not a multiple of 4, and take it with something with M, I end up getting everything, right? So for example, what I mean with that is, say I had an ideal that contained 6, well then 6 minus 4 would have to be in there, so 2 would have to be in there, right? And if once 2 gets in there, all the multiples of 2 are in there, so I get the whole ring. Okay, so if you've got something that's a multiple of 4, and something that's 2 more than a multiple of 4, what am I going to end up with in there? Well, notice that what would be the GCD of these two things? 2, right? So there'd be a linear combination that gives me 2, right? I get a linear combination that gives me 2, which is a problem, isn't it? Because if I get a linear combination that's 2, it puts 2 in the ideal, which means it's everything. Okay? So in particular, M is a maximal ideal. Oops. Oops. Of E. What about E mod M, though? How many elements does E mod M have? Well, how many distinct cosets are there? Well, you've got the coset that is just the entire maximal ideal. And you'll have the coset that's generated by 2, and that's it. Either you're a multiple of 4, or you're 2 more than a multiple of 4. That's what that says. It splits it into 2 sets, correct? Right? Now, remember the previous theorem said that if M is maximal, then R mod M is a field, but we needed a commutative ring with identity in that case, right? To get that to work. Here's the problem. What happens when you take 2 plus M times 2 plus M? What do you end up with? Well, remember these are cosets. It's 4 plus M, but 4 plus M is the same thing as 0. Yeah. So in the factoring, what do we have? We've got a product that equals 0. Are the factors 0? Or is either factor 0? No. So is this even a domain, let alone a field? No. Okay. So even though M is maximal, E mod M is not a field. In fact, every product in M is, or E mod M is 0. We get a ring. You call that a ring with 0 products. Every single product that you can possibly form is 0. So we have 0 products. The reason why it doesn't contradict the theorem is because the theorem says we need a ring with identity. And we don't have a ring with identity here. So you don't get the same result. I know that was a lot. It's a hard theory day. Hopefully next time I've got some toys to play with. I brought them today. I thought we might get a chance to do them, but we didn't get a chance to. So we'll have some toys to play with. We're going to switch gears and start talking about groups. Oops, and drop my water bottle.
Finally, like we've been talking about how we're going
to talk about groups. I know we're talking all along about how we're going to talk about groups. We're going to talk about groups next time. Let me give you some homework problems to work on because I know you're dying to do some homework, right? Let's do 4, 7, 17, and 20 to turn in. All right. So again, this will be the last section that's on the exam in 2 weeks. Okay. So we'll start groups on Thursday, and we'll do group stuff for the rest of the semester.
Is the exam in 2 weeks or next week?
2.
2 weeks?
Yeah. Because advising day is in 2 weeks.
Yes.
Yes. Yeah. So 2
I
weeks.
had it in my calendar.
Yeah. So advising day is in 2 weeks. I wish they would have made advising day this coming Tuesday because that would be
Yeah,
make
that
it
would be
easier for voting. But what?
Why didn't they figure it out?
If it was the 1990s, that would make us groupies.
All right. Anyway, have a good one.